So, you ever wonder how the massive power from the grid actually makes it to your neighborhood safely? Well, it all happens in these incredible places, electrical substations. Today, we're going to roll up our sleeves and walk through the exact step-by-step calculations that engineers use to design these things. This is the real deal engineering workflow. Let's dive in.
All right, here's our game plan. First, we're sizing the transformer. That's the heart of the whole operation. Then, we'll figure out the system currents. After that, we'll get into designing for short circuits, planning for the worst. Next up is sizing all the conductors and cables, and we'll wrap it all up with protection and final checks. It's a really logical process, step by step.
Okay, Section 1, sizing the transformer. And let me be clear, this is the foundation of our entire design. Every single thing we do after this point hinges on this one decision. How big does this transformer need to be? If you get this step wrong, honestly, the entire design is a bust. It's that important.
So, before we jump into the math, we gotta know what we're actually measuring. The size of a transformer is given by its MVA rating. That stands for megavolt amperes. It's what we call apparent power. You can kind of think of it like the total size of a water pipe. It's not just about the pressure, which you can think of as voltage, or the flow rate, which is like current. It's the combination of both. It tells you the absolute maximum electrical load that transformer can possibly handle.
And here it is. The calculation really starts with this beautifully simple formula. S equals V times I. So apparent power, that's S, is just voltage, V, multiplied by current, I. This little equation is the absolute cornerstone for figuring out our transformer's rating.
Okay, let's put some real-world numbers to this. Let's say our substation is getting fed by a 33 kilovolt line. That's our high voltage input. And we know it needs to handle a load that's going to pull a maximum of 500 amps, which is half a kiloamp. So you just multiply 33 kV by 0.5 kiloamp and boom, you get your answer. 16.5 MVA. That's it. That's the number you'd literally take to a manufacturer to order your transformer.
All right, Section 2. Now that we've nailed down our transformer size, that 16.5 MVA, we can move on to the next logical step. Calculating the system currents. We need to know exactly how much current is going to be flowing through this thing when it's just doing its job, day in and day out.
And this right here is the critical question for an engineer. See, a transformer has two sides, right? You've got the high voltage primary side where the power comes in, and the low voltage secondary side where it goes out. And the thing is, all the equipment, the wires, the switches, the safety gear, it's totally different on each side. So we absolutely have to know the current on both sides to get this right.
So, to find the current, we just take our original formula and flip it around a bit. But wait, there's one extra piece here. For a standard three-phase power system, and that's what pretty much all power grids use, we have to add this little guy, the square root of 3. It's just a constant that pops up because of the way the three electrical phases overlap. You just have to have it in there to get the right answer. It's essential.
Okay, check this out. When we run the numbers, look what happens. On the high voltage side, the 33 kV side, we get a current of 289 amps. But then, on the low voltage 11 kV side, the current shoots all the way up to 866 amps. This is so important. It perfectly shows a fundamental rule of transformers. When you step the voltage down, you have to step the current up. It's a trade-off.
Okay, Section 3. We know our normal currents now. That's great. But what happens when something goes horribly wrong? A lightning strike, a tree falls on a power line, a short circuit. For just a split second, the current can explode to levels that are just insane. We have to design our substation to survive that violent, absolute worst-case scenario.
Now, I know this might look a little intimidating, but trust me, we can break it down into 3 simple steps. First, we'll calculate something called base impedance. Think of it as the system's natural resistance to electricity. Then, we figure out the total system impedance. And finally, we use that to calculate the short circuit current itself. Easy enough, right?
All right, step 1. Calculating our base impedance, or Zbase. And don't let the word impedance scare you. It's really just a technical term for the total opposition to current flow in an AC circuit. So by running this calculation, voltage squared divided by power, we get a baseline reference value for our system, 66 ohms.
Okay, step 2. Now we need the total impedance of the system during a fault. This includes the impedance from the whole grid feeding our substation plus the impedance inside our own transformer.
Now, you'd usually find the specific value on the transformer's datasheet, but a pretty common value for a transformer this size is around 10% of the base impedance. So that gives us a total of 6.6 ohms. That's the number that's going to try to hold back that massive fault current.
And here we go, the moment of truth. We just use good old Ohm's law. Current is voltage divided by impedance, and we calculate our short circuit current. And look at that number, 5,000 amps. Wow. To put that in perspective, that is almost 20 times our normal operating current. This is the single most important takeaway here. Every single piece of equipment in that substation, from the biggest bus bars to the smallest switch, has to be able to survive this massive, violent surge of power without, exploding. This is all about safety engineering.
Okay, on to section 4. So we've got our normal currents and our massive fault currents figured out. Now it's time to build the actual pathways for all that power. We're talking about sizing the physical hardware, the copper and aluminum superhighways that are going to carry all this electricity.
So let's start with the absolute backbone of the substation's wiring, the main bus bar. The big question is, how big does it need to be?
Now, you don't just pick a bus bar that matches the normal current. No way. You have to build in a safety margin. So a really common practice is to pick a standard size, say a 2,000 amp bus bar, and then apply what's called a derating factor. Here we're using 0.8. This basically accounts for real life. Things like hot summer days that can actually reduce how much current a conductor can safely carry. So that gives us an effective rating of 1,600 amps, which, as you can see, is way above our normal 866 amp current. Plenty of headroom.
Now, for the actual feeder cables that leave the substation and head out into the world, it's not just about the current. You've got to think about a few other things. Of course, there's the rated load current, but you also have to account for the voltage drop, how much voltage you lose over the length of the cable. And super important is the installation method. Is it buried underground? Is it hanging in the air? Both of those affect how well it gets rid of heat, which changes everything.
So let's bring this all back to our actual numbers. Remember that 289 amp current we calculated for the primary side? Well, after you look at all the engineering tables and consider all those criteria we just talked about, a good choice would be a 400 square millimeter aluminum cable. See? This is where all those calculations finally connect with a real, physical piece of equipment.
All right, we're in the home stretch. Section 5, protection and final checks. We've done all the heavy lifting on sizing everything. Now it's time for the final, critical stage. This is where we layer on all the protection systems and do the final checks to make sure this substation is going to be safe, efficient, and super reliable for years and years.
So one of the big final checks is efficiency. The truth is, transformers aren't 100% perfect. They always waste a little bit of energy as heat, and that waste comes in two main flavors. You've got copper losses, which happen because of the current flowing through the wires, so they change depending on the load. Then you've got core losses, and these are constant. They happen 24/7, just from the energy it takes to magnetize the steel core. And let me tell you, for a utility company, cutting down on these losses over the 30-plus year life of a transformer can save an absolutely massive amount of money and energy.
And this is it, the final settings. This is like dialing in the controls. We're going to set our main and feeder circuit breakers to trip at specific currents. That's our ultimate safety net. We'll double check that our earthing system has a super low resistance, under 1 ohm, so any fault has a safe path straight to the ground. And finally, we set the tap changer. This is a really cool device that lets the transformer tweak its voltage ratio just a little bit, all by itself, to keep the voltage going out to customers nice and stable, even if the main grid is fluctuating.
So, let's just do a quick recap of the whole process. Remember, it all starts with the transformer's MVA rating. That's our foundation. From there, we calculate both the normal current and that huge fault current. We then use those numbers to size our conductors for the absolute worst-case scenario. And finally, all those last checks and protection settings are what guarantee long-term reliability. That's the workflow in a nutshell.
And there you have it, a step-by-step guide to the core substation design calculations. But it does leave us with a really interesting question for the future. Substations aren't just one-way streets for power anymore. So think about this. What happens when you add a massive battery storage system? A system that can both suck down huge amounts of power and push it back out. How would that completely change the fundamental design calculations we just walked through? Definitely something to chew on.